Hello and welcome to this fourth lesson. Last time we were looking at successive ionisation energies, so that's looking at a single atom and removing more and more electrons. This time now we're going to look at trends in the periodic table, and the graph that we can see on the screen at the moment is the graph of the first ionisation energy for all the elements in period 3, so going from left to right across the periodic table. And so essentially we're looking at the elements in each different group successively. So in fact if you look at the atomic number on the x-axis, I suppose if you take 10 off the atomic number you'll effectively have the group number, or certainly as we see it in GCSE, group 1, group 2, group 3 up to group 8 on the right. So our group 1 element there will be sodium, then it'll be magnesium in group 2, aluminium in group 3, silicon in group 4, phosphorus in group 5, sulfur in group 6, chlorine in group 7, and then argon there in group 8, or the noble gas. So looking at this graph, there are essentially three features. So yeah, it holds a huge amount of information, this graph actually, and in describing those three features we're going to cover a great deal of atomic structure, and that's the reason these graphs very often come up in exam questions. So the most basic feature to explain is the fact that as we go across the period from left to right, the ionisation energy is, roughly speaking, increasing. There's a general increase in the ionisation energy. So we need to be able to rationalise this. And we can do this in terms of shielding. So of course, as we go from one element to the next, as you go across the periodic table, we've got one more proton in the nucleus each time, one more electron going into the outer shell, the valence shell, each time. And so the real clincher here is that those outer shell electrons are not shielding each other very effectively. So the extra charge in the nucleus is only very slightly reduced by the presence of another electron in the outer shell. So as you go from left to right across the period, the valence electrons in the outer shell are experiencing a greater nuclear force. And so experiencing a greater nuclear force, they're held in more tightly then to the nucleus, and for that reason you need that much more energy to get one of these electrons out. So to ionize the electron we've got to raise its energy essentially up through all the higher shells which are vacant to a kind of freedom on the outside of the atom, which is like the infinitieth shell, because these shells, their energies get closer and closer together and converge to a limit where the electron is free. So as we go from left to right across the period, the electrons are kind of pulled lower and lower down in their energy as they get more and more attracted to the nucleus, and they're harder and harder to pull out of the atom. So it's this ineffective or this inefficient shielding that the valence electrons do with each other that means that the electrons are held in more tightly. And having got the idea of the general increase, we then need to look at these discontinuities. So you see that going from group 2 to group 3 there's a drop in the ionisation energy, and likewise going from group 5 to group 6. So if we turn first to the drop from group 2 to group 3, this is going from magnesium to aluminium. So the significant thing is, as you go from group 2 to group 3, magnesium to aluminium, you're moving from the left hand side of the periodic table, the S block, over to the P block on the right hand side, which means the highest energy electron is now in a 2p subshell in the case of aluminium, rather than in a 2s subshell in the case of magnesium. And we know from the Aufbau principle we fill the 2s before we fill the 2p, and this is because the 2s is lower in energy. And so when you go from magnesium to aluminium, if you like, the highest energy electron, sort of the outermost electron, is at a higher energy in the case of aluminium, and because the electron is at a higher energy, you don't need to put so much energy in to take it up to the limit. And so that discontinuity from group 2 to group 3 reflects the fact that you're now filling a subshell that's higher in energy. So that's the first discontinuity there. And so this really hinges upon the different energies of the subshells. So it kind of relates back to the Aufbau principle. So on to our final discontinuity, going from group 5 to group 6. And to understand this, we need to think back to what we did about electrons in boxes. That's to say, how the individual orbitals are occupied. So nitrogen has got 3 electrons in the 2p orbital, in the 2p subshell, and the 2p subshell has got 3 orbitals in it. And so we know that we feed those electrons into separate orbitals. So those 3 electrons will all be spin parallel in separate orbitals. And so actually when you get to oxygen, the 4th electron along in the p subshell, we get a bit of a discontinuity here, because for the first time you get a pairing up of electrons. That 4th electron has to go in and pair up with another electron in one of those p orbitals. And so again, that's kind of a new phenomenon going across the subshell, the 2p subshell. And so when we pair the electrons in a p orbital, those electrons being closer together, they experience more electron-electron repulsion. And this repulsion raises the energy of the electrons. And having raised the energy of the electrons, of course, again, a bit like we said before, it lifts the energy up closer to that ionization limit, where the electron is free altogether from the atom. And so, obviously, as we continue to the end of the 2p shell, there's going to be more and more pairing of electrons. But the one that's the discontinuity, as I say, is when you go from no pairing to pairing. And that's where you see the sudden step up in energy. So the step up in energy of oxygen's valence electrons corresponds to the step down in the ionization energy, the extra energy you need to add for the electron to escape the atom. So there we are. That's the trends in ionization energy across a period. Now, in this next slide, still sticking with ionization energy trends in the periodic table, now we're going to look at the trend down a group. And so I've chosen the alkali metal group in this case, so it's the alkali metal data we've got on the graph. So on the x-axis we've got the period number. So our first alkali metal will be lithium, and lithium is in period 2. So that point there on the left hand edge of that curve, that corresponds to lithium. And so then now as we go from left to right on the graph, we're stepping down the alkali metal group. So period 3 will be sodium, period 4 will be potassium, period 5 rubidium, period 6 cesium. And so this is a simpler one because we don't have any breaks from the trend. We see that the ionization energy is simply going steadily downwards as we descend the group. So as we go down the group, obviously what the alkaline metals have in common is they all have a single electron in their valence shell. But of course the difference is that that valence shell is one shell higher each time. And so the number of the shell corresponds to the period number. So in the case of lithium, its outer electron is in the second shell, the 2s orbital, sodium 3s, potassium 4s, etc. So we're looking at a higher shell each time. And so this is the really significant bit. It's to do with the fact that we have to consider not only have we got extra protons going in the nucleus, so for example if lithium is element number 3 and sodium is element number 11, that's a jump of 8. So there's 8 more protons in the nucleus for sodium, but sodium also has 8 more electrons. And the big difference here compared to the trend going across the period is that those 8 electrons are inside the valence shell. They're core, as it were. They're not in the valence subshell, they're internal in the atom. And so where the electrons are internal in the atom, they do a much better job of shielding the outer electrons. And this is because they're between the outer electrons and the nucleus, effectively, most of the time. So that electric repulsion that the outer electron experiences from the inner electrons, that counteracts the electric attraction that the outer electron will have to the positive nucleus or if you like, to the extra protons in the positive nucleus. So to quite a large extent, these inner shells of electrons that appear as you go down the group are to quite a large extent cancelling out the effect of the extra protons in the nucleus. And so if we assume that the extra electrons in the atom are cancelling the effect of the extra protons in the atom from the point of view of the outer electron, the electron that's going to be ionised, you might assume therefore that the ionisation energy is going to be a constant down the group. But really, as we go down the group, the most important thing is that that outer electron gets successively further away. So the third shell is further from the nucleus than the second shell, and likewise as we go to higher shells we're further and further from the nucleus. So even if the outer shell electron experiences roughly the same nuclear charge as you go down the group, the fact that the outer electron is further and further away from the nucleus means that the force of attraction to the nucleus is going to be weaker for that electron. And this is very much in line actually with the chemistry that's observed. So if you think about these alkali metals, those elements, when they do a chemical reaction, they're always going to end up as a 1+ ion, aren't they? And so at some point in the chemical reaction they're going to have to lose that outer electron, and so the energetics of taking off that outer electron are going to be reflected in the ionisation energies. So down at the bottom of the group there with cesium, you've got a small ionisation energy to remove that electron, so that's kind of consistent with the idea that the activation energy for cesium is likely to be quite small. There are other factors as well, but at least this is consistent with that. And so this is also consistent with our observations in the lab that, you know, cesium is dangerously reactive. You might have seen a video of it in water. You won't have seen it for real because it will cause an explosion. It's so reactive. Whereas the lithium, on the other hand, will bubble away, you know, much more sedately. That reflects the fact the activation energy is higher, which is, yeah, in some sense related to the fact that it's harder to get the electron off lithium, really, because the electron is that much closer to the nucleus. And then finally, a quick word about atomic radii. And really this is because the radii very much reflect the ideas that we've been talking about with the ionisation energies. So we said, for example, when we were explaining the increase in ionisation energy, generally speaking, across period 3, we were saying that as more protons go into the nucleus in those atoms, as we go from left to right across the period, the outer electrons experience a greater attraction towards the nucleus because the additional electrons are not shielding very well the additional protons in the nucleus. So it's consistent, I think, that since we observe that those outer electrons experience a greater nuclear attraction, reflected by the increasing ionisation energy, it's kind of logical then, isn't it, that they get pulled in a bit closer to the nucleus. So following this logic, it follows then that we'd expect the radius of the atom to shrink somewhat as you go from left to right across the period. And so this is reflected in the graph there. And so it's a common error for students actually to assume the opposite is true. Because, you know, naively you'd first look at the periodic table going from left to right across a period. You'll say, well, there's more particles present. You know, we've got more protons, more electrons, probably more neutrons as well, more stuff there. So presumably it's bigger, but it doesn't actually work in this case because the way the particles are arranged, specifically with electrons in shells, it turns out that as we go across the period, those electrons experience a greater nuclear attraction. So it actually causes the atoms to shrink. There we go. So I've made that point there in this bit of text here, just consistent with our ionisation energy trend. And similar sort of thing when you go down the group as well. So again, I've chosen the alkali metals, and we see here that the atomic radius gets larger as you descend the group. And of course, this is entirely consistent with what we were saying about the alkali metals before. That's to say, the outer electron is in a higher shell, the higher shells are further from the nucleus, and so it kind of is obvious really that the atoms must be getting larger if the electrons are in higher shells, and this is exactly what's observed, and so we see that on the graph there.